does it mean? It means the minimum n such that for every colouring of the edges of Kn with two colours, there exists either colours. Yes. And yes. Either a red copy of G or a blue copy of H. Does it make sense? So you're going to you colour all the edges of the complete graph, and you're looking for either a red G or a blue H. So in the case in the lista, G is a triangle, so you're looking for a red triangle or a blue copy of the tree. Okay. Are there more questions? No? Okay. Did everyone receive the lista?
No.
Ah. Okay. Did you email me?
No.
Ah, okay. So. Okay, so I think we have a solution. What else? Oh, I told you we were going to re-vote once there are fewer people. It looks like there's fewer people now. So, so who votes that we stay speaking English? You can only vote once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think that was 1. Who votes Portuguese? Yeah, it doesn't. Okay. Okay. Right. So we're going to talk about the chromatic number of a planar graph. So recall definitions. So a graph's planar if you can draw it in the plane without two edges crossing. So this is forbidden. And definition, the chromatic number of a graph is the minimum R such that there exists a colouring of the vertices of G with R colours such that the endpoints of edges get distinct colours. Okay. So it's a famous theorem four-color theorem, proved in the 70s by some people I've forgotten, sorry, that for every planar graph, the chromatic number is at most 4. The proof is an extremely complicated case analysis, which was done partly with a computer. So the guys who solved it, they reduced the problem to 2,000 cases or something, and then instead of going through them one by hand, they just plugged them into a computer. So it was an early application of computer-aided proofs. So it's kind of boring, right? It's unfortunate. It's true. But there's no really good reason it's true. The proof doesn't tell you why it's true. It just says, okay, we're going to check all these cases, and oh, look, it happens to be true. So it would be nice to have a good proof of this, a proof that told you why it was true, though, I mean, maybe it's just not the case. Maybe it's true because these cases happen to work, right? It's just an unfortunate example. Anyway, so we're not going to prove this, thank goodness. We're going to prove something weaker. So our aim is going to be to prove the chromatic number is at most 5. Okay, so first, let's just have an observation. The chromatic number of G, so G planar, implies chromatic number of G is at most 6. What's the proof of this? This was homework, right? Yeah, okay, so how do you do it? Mm-hmm. On what? Mm-hmm. Number of vertices of G. N at most 6 is okay. Okay, so how does the induction step work?
You use that formula of the number of the bounded.
Right. So we proved last time the edges of G was at most 3n minus 6. What does that tell you?
You can see the mean degree.
Right. It implies the minimum degree is at most 5. Why? Because if every vertex had degree at least 6, then the sum of the degrees would be at least 6 times n, which means the number of edges would be at least 3 times n, and it's not. Is it okay? Okay. So, yeah, let me do it here. So if the degree of V is at least 6 for all V in G, then the sum of the degrees is at least 6 times n, and this equals twice the number of edges. Okay, so we have a vertex of degree at most 5. There it is. Remove it. Yeah, so let's let G prime be G minus V. So here's G, and then we just remove V.
Then G prime has a most 6 color.
Right. By the induction hypothesis, we can color G prime with at most 6 colors in a proper way. Proper will mean, so a coloring that satisfies this, I'll call a proper coloring. I don't know what a good translation for that is. Proper. Anyway.
Then when you put back V, it only has 5 neighbors, so there's always one color available.
Exactly. So just look at the neighbors of V. There's only 5 of them. Maybe their colors are whatever. There's always a color available. So you can always color this last vertex. Okay. So more generally, a fact, an observation. For any graph G, the chromatic number of G is at most do I really want to talk about degeneracy? Perhaps not. Yeah, so this is a quick aside. So the correct number of any graph is at most the maximum degree plus 1. So what's the proof of this? Sorry?
You start coloring?
You just start coloring, right? Just color, pick a vertex, color it, pick a vertex, color it. Just make sure you don't screw up, right? Don't color an edge monochromatically. And why do you never have to screw up? Because whenever you come to a vertex, even if all of its colors, or even neighbors are colored already, there's always a color left because you have more colors than the degree of a vertex, okay? This is called the greedy algorithm. So you just color, just don't even think about it. Just like check that at each step you don't mess up when you don't have to. Okay? So perhaps you could think about, so this is a bit weaker here. Here we had a maximum degree, and here we just needed the minimum degree. So you might think a little bit about how you could improve this bound using this kind of idea. Worth pondering. Anyway, let's go back here. Okay, so this is true. How about now we prove the 5-color theorem? Okay, so once again, I've not erased this proof for a reason. If you have a proof of something slightly weaker, you can try to strengthen it, right? So what does this proof of the 6-color theorem tell us about our attempted proof of the 5-color theorem? So, suppose you want to prove the 5-color theorem, how might you go about it? You could start the same way, right? You could try and do induction on n. You'd notice for n at most 5, it's true. You'd notice that, as before, you have a vertex of degree at most 5. You can look at this vertex. You can remove it. You can color G prime by induction. You can put it back in. When are you done? When are you happy? Or when are you not happy?
All these colors, the remaining vertices are different.
Yeah, exactly. You're happy unless V has degree exactly 5 and the coloring of G prime gives them all different colors. Right? If they only used 4 colors, you'd have one left. Okay? So let me redo this picture. So I'm going to want to expand it now. Okay. So here is G. Here is V. Maybe I'll do the 5 neighbors first. Then write V. And here is neighbors. And without lost generality, you can assume that they are colored 1, 2, 3, 4, 5. Okay? In the coloring given to us by the induction hypothesis. Okay so far? Okay. So now what do? Now we need an idea. Right? Who has an idea? Mm-hmm. Yeah. Right? Exactly. I mean, in some sense, what else can we do? We need to change one of these colors. Right? We need to find a coloring of the rest that doesn't have this property. So, okay, let's suppose we want to change the color of this guy too. Okay, I'm just going to try and change it to 3. Okay, now we're done. Okay, we're done unless this guy has a neighbor who is colored 3. Okay, so we're moving back to 2 again. Okay, so I wanted to change the 3, but I couldn't because there's a neighbor colored 3. So what now?
Try with another color.
Right, so let's sort of think we're trying this in all of these, and so for every pair 2, 3, every ordered pair, we're going to try this. But let's just focus on 2 and 3 for now.
You change the other 3?
Yeah, right? Right? Let's change this to 3 and change that one to 2. And then we're okay. There we go, now we're done. Right? Unless this guy has a neighbor colored 2. Now we're in trouble again. Okay, let's change them back. Okay, so let's carry on. So what happens? Right. So there are 2 things that can happen. Either this stops at some point, in which case we're happy because we can just flip everything, or it doesn't, in which case it must reach this guy.
Why must it reach that vertex and not a cycle between one of those other vertices?
Okay, so good question. So let's write down what we really mean. So let's define H 2, 3. Right, so I'm starting at 2 and I'm trying to change to 3. So be the component, the connected component I mean. Ow, what have I done? Ow. Pulled a muscle in my arm. My goodness. Okay, this is not going to be much fun to write now. Okay. Ow. I might start writing lower. The connected component of the graph formed by the vertices of colors 2 and 3 and containing this vertex. Let's maybe call this one, let's call them U1, U2, and so on. Does it make sense? So we just look at the vertices with colors 2 and 3. So they form various connected components. Right? There are various subsets that are connected and disconnected from each other. And one of those contains this vertex U2 because it's got color 2. So let's look at that one. So here is H2, 3. Okay, so there are 2 cases. Case 1 is that U3 is contained in H23, and case 2 is that U3 is not contained in H23. Okay, so why are we happy in case 2? Yeah, you just flip the colors of all the vertices inside here. All the 2's become 3's, all the 3's become 2's. So you have no monochromatic edge because there's no vertex of color 2 or 3 that's connected to this thing. Right? That's how it was defined. Does it make sense? So in case 2, so inside H23, swap the colors 2 and 3. This guy swaps color, and this guy does not. So now this guy has 2 neighbours who are 3, so he can be colour 2. Is it okay? Okay, so what about case 1?
We pick another hij.
Right. So we can do this for every ij. So in fact, this argument holds for any pair 2 and 3, right? So really, these are not the correct cases. So perhaps I should... I'll call them A and B. Now really the cases. So case 1 is that there exists I and j such that uj is contained in uij. In this case, we exchange the colours I and j inside hij.
You mean uj not in aj?
Thank you. Thank you. Right. And give colour. So what happens? Colour vertex I becomes j. Okay, and set the colour of V to be I. Right? Is it okay? Okay, this is the same argument. Okay, so case 2. Uj is in hij for all pairs I and j. What do you want to do?
Maybe it has a K5 inside and it's not clever.
Right, so that's a very good observation. So as we saw last time, K5 is not planar, and we have 5 points, and each of them are connected to each other by paths. We say it's okay, it's also the same as if they're topologically. If there's no topological K5, so even if they're paths rather than edges, it's also true. But in that definition, the path shouldn't contain the same vertex. So why can't 2 of these paths between things contain the same vertex? Right, so if they're using different colours, then they can't. But some of them are using the same colours. So I think it doesn't quite work. That's the right idea. So let's do it more directly. So let's use that idea. 2 paths that are using different sets of colours cannot cross. Give me 2 paths which use different colours and have to cross in this picture. Say it again? Yeah, exactly. Right? There's a path in H52, so a sort of 2-5 path between 5 and 2. And there's a 1-3 path between 1 and 3. But these paths are not allowed to cross. Right? And they can't use V. So there's a contradiction. Okay? So so H25 and H13 are vertex disjoint. There's a contradiction. Okay, you can't get from questions.
I'm curious how I would write this now rigorously. This last argument.
Yeah, so it's sort of annoying. I mean, this is completely obvious from the picture, right? So there's some art in conveying a proof in words that's really a picture.
Will you be satisfied if we put on the picture?
Yeah. I mean, that's the proof, right? For me, that's the proof.
No, I'm satisfied.
Right? Yeah. Yeah. So right. So what is a proof? In some sense, it's something that satisfies the audience, right? Yeah, so I mean, I guess really all this is being done in the plane, and therefore we have to somehow use the axioms of the plane. So are we using like the Jordan curve theorem or something like that? I don't know. But I mean, it's obvious in this case, right? It's not, yeah. So I agree there are many cases in which one should really be careful, but here it's sort of obvious. Questions? Okay. Right. What else do I want to tell you about chromatic number? So chromatic number. Yes, I don't really want to spend much time on planar graphs. I want to tell you a little bit about that they exist. There's a problem on the example sheet about them. But mostly this course is about much denser graphs. So maybe I'll return to much denser graphs now. Huh?
Why you can't move on with these ideas to prove chromatic number for?
That's a very good question. So in fact, the guy who proved this thought that he'd proved the four-color theorem. So he fooled himself into thinking, I'm not sure exactly quite how, but this was published as a proof of the four-color theorem, and no one spotted it for quite a while, that it was wrong. So what goes wrong? So I guess you might want to try to swap two of these at the same time. And maybe you can under many circumstances, but they're presumably examples of small graphs where this doesn't work. And as I understand it, the proof then goes into an analysis of all of the different ways in which this proof can fail, or perhaps some more complicated version of this proof. And perhaps the best way to convince yourself is just to try it. So try to write down a proof of the four-color theorem with this, and you'll probably bump into exactly these kind of examples. I mean, I don't suggest continuing until you have all 2,000 examples or whatever. But perhaps it will become clear that this sort of low-dimensional world, then things can be sort of annoying and complicated. Like small examples can really mess you up. Yeah, so a high-dimensional world is a bit cleaner and simpler and that's more random-like. Right, so we'll return to extremal graph theory. I'll talk about the Erdös-Stone theorem, proved in 1946. That is sometimes called the fundamental theorem of extremal graph theory. So what it gives an sometimes asymptotic for the extremal number of any graph H. Well, you'll see that's not quite true, what I said. So, can you give me a lower bound on the extremal number of H that holds for every graph H. So there's a hint that there's a definition on the left. There's two definitions on the left. Perhaps I'll erase the one that you're not going to use. So can you see how to construct a graph that avoids H with many edges given its chromatic number? So I should write H instead here. I'll change this to H so it's more obvious that's what we're doing.
You that graph with chromatic number which is less than H.
Yeah, exactly. So if we have a graph with chromatic number less than H, it cannot contain H. Right? So what's a graph with many edges and chromatic number less than H?
Potatoes.
Yeah, potatoes, right? Potatoes. It's always potatoes. What's the chromatic number of this graph? Number of potatoes, exactly. Right? This is a four-partite graph. You can colour, so just in case it's not clear, you can colour each potato with a different colour. Every vertex inside with a different colour. Right? So if the chromatic number of H is 5, it's not contained in this. Right? So what does that tell us? Because so suppose you could find a copy of H inside here. You have to put some of its vertices here, some here, some here, and some here. And then you'd have a colouring of H with 4 colours. And there's no edges inside here, so there's no edges inside H in this part. Whereas if you found H here, this would give a colouring of H. Yeah. So in other words, so observations about this, H is contained in G implies chromatic number of H is at most chromatic number of G. Perhaps it's more obvious. The more edges you have, then the more restrictions you have. Right. So what does this tell us? It tells us that the extreme number of H is at least the number of edges in this guy with chromatic number minus 1 parts. How many edges does this guy have if it has chromatic number minus 1 parts? So if it has r parts, all of size n over r, then what was it? It was n over r squared times r choose 2, which is r minus 1 over r times n squared over 2. Right? And r should be chromatic number minus 1. So this proves is at least 1 minus 1 over chromatic number of H minus 1 times n choose 2. That's not the theorem. That's an easy observation that we just made. The theorem is that this is the correct answer. Okay? You can't do better than this. In the following sense, if we add a little O1 here, then you can't do any better. Okay?
So it's equal, right?
Thank you. Okay. Now, I want to give 2 proofs of this during the course. The second proof will be using something called Szemeredi's regularity lemma, and will be towards the end of the course. And will be it will be very short and simple, given some machinery that we'll build up. But perhaps so you appreciate that proof properly, I'd like to now give you a sketch of the Erdös-Stone proof, which is much more complicated. Now, I'm a bit worried to do this because it's a bit scary, right? So I don't want you to think that if you get confused by this proof and find it very complicated, then, oh my God, from now on the course is going to be super complicated and it's over, right? So this is a complicated proof. I'm not expecting you to reproduce it in an exam. I'm not even necessarily expecting you to follow all the details. Just want you to see kind of how an argument like this could go. Right? So please don't be too scared by it.
I have a question. I'm confused because we have seen that if H doesn't have cycles, then the growing is linear, but it seems to be quadratic.
Good question. Thank you. Very good question. What's the answer? When is this quadratic?
When the little one is not decaying fast, for example, say.
So little o1 is always going to 0.
Chromatic number is bigger than 1.
Yeah, 2, right? So if chromatic number, so yeah, thank you. This is something I should have said before, but I suppose we'll see it in the proof in a second. If the chromatic number is 2, then what does this say? 1 minus 1 over 2 minus 1 is 0. So it says exactly that the number is at most 2 if and only if the extremal number of h is little o(n) squared. And what's the chromatic number of a tree? Ooh, good question. What is the chromatic number of a tree? So lemma. I get most. 2. And what's the proof? Start colouring. Yeah, so what we do is remove a leaf, right? So every tree has a leaf. By induction, you can colour this with 2 colours, and then this gets the opposite colour from that one. So this is in a special case of a more general idea that we used in the proof before. Another proof of this that I quite like, just perhaps I should tell you. So the induction proof is fine. So proof 1, induction. Proof 2. This is a nice idea because you see this idea used other times. Let's start with a vertex. Look at its neighbours. And then look at the second neighbours, the neighbours of these guys. And the neighbours of those guys, and so on. Until you get to the end. What's the colouring?
Alternate.
Yeah, just alternate, exactly. This guy's yellow, this guy's green, this guy's yellow, this guy's green, and this guy's whatever it happens to be. And why are there no edges, monochromatic edges?
Each set is an independent set because if not, there would be a cycle.
Exactly, exactly. If you ever had an edge, yeah, please.
This last observation is a weaker result than the first result about trees, right? About a graph without cycles, right?
So if the graph doesn't have a cycle, yeah, it's much, much, much weaker. Very little o(n) squared, and really we prove that these have extremal number linear. Yeah, so it's way, 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 way weaker. It's even much weaker than the proof, what we proved for graphs, for bipartite graphs, as I'll remind you in a second. Yeah, so more is known, yeah, exactly, in the bipartite case. Right, so there's no edges inside, and there's no edges sort of between here and here, because otherwise this vertex would not have been here, it would have been here. Right. Okay. So let's recall that even more. Yeah, so if chromatic number is at least 3, however, this tells you what the extremal number is asymptotically. It tells you it's quadratic, and it also tells you the constant in front of n squared. Right? It tells you the extremal number up to a factor of 1 plus little o1, which is pretty nice. So recall Kovári-Sós-Turán. So this is sort of silly. This was done in the 50s and this was done in the 40s. But I think this was just published in the 50s. I think it was done earlier. But anyway, so they proved that the extremal number of the complete bipartite graph is at most what? It was most some constant depending on s and t times n to the 2 minus 1 over s. Right? We proved this a week ago or so. Perhaps I should start by reminding you of this proof. Who remembers how to prove this?
Counted cherries.
Yeah.
Cherries.
Yeah. That sounded like no one else remembered. Does everyone now remember? Sure. Okay, I'll do it very quickly in that case. Okay. So yeah, it's nice to prove this again, just because the proof of this is sort of a generalization of the proof of this. And this will also act as the base case of our induction. Right. So what was the proof of this? So we count copies of K1S. Right? This is an S cherry. It's a vertex with S neighbors. So the number of K1S's, which is equal to the sum over vertices in G of the degree choose S. That's counting from the top, and is at most t minus 1 times n choose S if there does not exist KST. Right. Okay? This thing, by convexity, so Jensen or whatever, is at least n, number of vertices, times the average choose S. 1 over n, sum of the degrees, choose S. Right? This thing is twice the number of edges, equals n times twice the number of edges of G, choose S, and that gives you an upper bound. Right? I mean, over n, sorry. Yep.
How exactly you get the upper bound?
This one? Right, so we're going to count from the bottom. So how many different K1S's can sit on a set of S vertices? So given a set of S vertices, how many can sit on it? At most t minus 1, because each one gives you all the edges across. Right, if you're t of them, you just...
And to last step, how do you get from counting cherries to the bipartite graph?
Right. So if H is bipartite, then it's contained in KST for some ST. For example, if you take S equals T equals the number of vertices of H, then it's definitely contained there. Right. Okay? Yeah, so we're going to do the same trick with Erdös-Stone theorem. we're going to first put our graph H inside a complete R-partite graph where R is chromatic number minus 1. Sorry, it's chromatic number. So let's fix a graph H with chromatic number 3. And let's just try and prove chromatic number 3. Okay. Chromatic number of H is going to equal R, which equals 3 in this case. Okay, let's just try and prove for 3. And you'll see that the proof generalizes. I think once you see the proof for 3, you can believe that you can write down a proof in general. The pictures will be simpler for 3. Okay, fix that maybe. And let's say, therefore, that H is contained in the graph K, T, T, T for some T. Okay, let's just pick T such that this is true. Okay, given any 3-partite graph, any graph with chromatic number 3, there exists a T, most of them are vertices of H, such that this is true. Okay? Just given by the coloring with 3 colors. You look confused, so I'd like either questions or nods.
Can you repeat it again?
Yeah. So this means that there's a coloring of H with 3 colors. 1, 2, 3. So that all the edges go in between the parts. There's no edges inside. So if we let T be the maximum of these 3, then this is contained in the complete 3-partite graph with T vertices in each. Right? Okay. So just a trivial observation. So let's, instead of finding H, let's find KTTT. Okay. Okay. So how are we going to do this? So we need induction on R. We've already proved the result for R equals 2. Okay. And by the way, I'm going to give a proof that doesn't work, and then we're going to come back to the beginning and try and fix it. Okay? So really I should do something a bit weird at the beginning, but let's wait until we need it, and then you'll see why. Okay. So how might we go about it? So what can the induction hypothesis tell us? It can tell us, so we know we've got, so what have we got? We've got E of G is at least 1 minus 1 over 3 minus 1, so half, plus a bit times n choose 2 edges. So a half plus, let's say, call it alpha, n choose 2 edges. Okay? And we want, yeah?
You say that we will fix R and then we will do induction on R.
Yeah, so let's suppose we're trying to prove for R equals 2 and 3. So the base case is 2 and the induction step is 3. But you'll see that it generalizes. Yeah, so the proof in general is by induction on R. We're just going to do the first step. Yeah. And it's mainly for the pictures, the main differences. I don't want to have to draw more than 3 blobs. Yeah. Okay, so we've got a graph with this many edges. We want it to contain KTTT. Okay? But alpha is arbitrarily small. So. And n goes to infinity. Okay, so we're given T, we're given alpha, and we take n large. Okay? So what can we use the induction hypothesis for? Mm-hmm. Yeah, so T is some integer. T is given. Alpha is given. So our bound, it can be anything arbitrarily small.
Alpha depends on
right, so alpha is going to 0 slowly with n, but if I can prove it for every alpha for n sufficiently large, then I can prove it for alpha going to 0. So it's enough to prove it for every fixed alpha. Okay. So we'll even give an explicit bound on n, the n we need in terms of t and alpha. So you'll see exactly what these things, what we prove these things are. Okay, so the induction hypothesis will give us a large complete bipartite graph. Let's suppose there's q vertices on each side. And I'm thinking of q as being much bigger than t. Well, I'm using this notation informally to just mean it's a much bigger constant. Though in fact, as we see here, really we could take it to be going to infinity. Right? I mean, that the extremal number of kqqq is much smaller than n squared. Right? And we have about n squared over 4 edges. Right? So we can find a very large complete bipartite graph inside G. Is it okay? By what we just proved, please. Yeah, so the extremal number of kqqq is the extremal number of kqqq, this thing that we're finding, is by the theorem we just proved, a most c some function of q times n to the 2 minus 1 over q. And I claim this is at most n squared over 4 for any fixed q, certainly, if n is large, and even if q goes to infinity very slowly. Right? So we can pick an arbitrarily large q, and this will be true, and we can find this guy inside G. Is that okay? Yep. Okay. So we find this guy. Okay. And then here's the rest of the world. Let's call it G prime. Now, what do you want to do? How do you want to find this KTTT? Yeah, what we want to find exactly is t vertices here, t vertices here, and t vertices here, such that they all send edges and they all send edges. Right? So this should look, I mean, what we're looking for is something that looks a bit like a kt2t. Right? So we're looking for that now, a complete bipartite graph, but with an extra restriction. We should have t on the left and t on the right. Okay, but we know we have at least one technique, perhaps we only know one technique so far, of finding complete bipartite graphs. What do we do? What's the only way we know of finding bipartite graphs? The one we just used. Yeah, counting cherries, right? The only thing we know how to do is count cherries. So let's try to count cherries somehow. So what do we mean by a cherry now? Yeah, it's a bit like a generalized cherry, right? So what we should probably try and do are count things that look like this. How many are there? Well, how many are there at most first? Or exactly. Okay, so we're going to count. So the number of things that look like this is equal to, is at most what? Uh-huh. Yeah, exactly. Right, summing from the top, choose this set, Q choose T, choose this set, Q choose T. It can be at most T minus 1, so you get this. This is if there does not exist KTTT. And what's nice about this thing is it's just a constant. Right? So I don't even care what it is. I'm just going to call it C. Right? It's just some constant that doesn't depend on n. Okay, and what is the number of these things equal to? Feel free to make up notation for whatever you need. What was the number of cherries equal to? Yeah, there's the number of cherries in the proof of this thing. The number of cherries was equal to what? Yeah, exactly. So I want something like this. So what is it?
You define T1 as the number of degrees that goes to that potato, and T2 to the other potato.
Yeah.
Then it's the sum
Yeah.
of T1 times 2. No. T1 chooses G times T2 chooses G.
Yeah. There you go. I mean, I call it DL and DR, but yeah, exactly. Yeah, so you degree left and you degree right. Okay, so that's good. So if we can show that this sum is bigger than a constant, we have a contradiction. That's what we need to do. Okay, that doesn't sound too hard. I'll get rid of this. Sorry, what I mean is in the vertices of G prime, right? Yeah. Okay. How are we going to prove that?
One of them is approaching infinity, and the other is
So in both cases, why? So you'd made two claims.
Yeah.
Can you justify either of them?
Greater or equal to 1 because it's binomial.
So what is the binomial 1 choose 2?
That's not a lot.
I mean, what's the binomial 0 choose 2, right? Why is the degree to the right non-zero? Why is the degree to the left non-zero? Why is the sum of the degrees non-zero? Why are there any edges between the top and the bottom at all?
Because we have a bound of x for the edges of G.
So we do have a bounded number of edges. Why does that imply this particular copy of KQQ we found has any edges at all going down? Sorry? I mean, maybe all the edges on the bottom. Maybe we have some kind of some nice dense graph on the bottom, and then just a complete bipartite graph hanging out. It's got nothing to do with the rest of it. I mean, the answer is nothing stops it. It might happen. Right? We didn't do anything to prevent it. So the proof doesn't work. Right? We have to choose our complete bipartite graph more cleverly. We have to choose it. We have to make sure that we have lots of edges in between. Otherwise, we're not going to be able to prove this. OK, so let's go back to the beginning of the proof. Let's try to choose this complete bipartite graph so that this is true. How are we going to go about doing it? And note that we haven't used this property at all yet. Right? And we're going to need it because if alpha was 0, the thing could be bipartite. Right? So we really need to use this in a very precise form. I mean, we're going to use the alpha as positive. So, suggestions. So we want to find a complete bipartite graph that moreover has many edges going out of it.
Can we add edges?
No. Definitely forbidden. Right? So we don't know how to do that. Right? The induction hypothesis, it's a proof by induction. Right? The induction hypothesis, at least at the moment, just tells us we can find a complete bipartite graph if we have lots of edges. It doesn't tell us anything about the edges coming out of that thing, the degrees of those vertices. So if we want to apply the induction hypothesis, we're not going to be, as it is, we're not going to be able to apply it in G. Right? We need either a better induction hypothesis, which is a bit scary because we have to make up what it is and then prove the conditions at all levels, or we have to apply the induction hypothesis as it is in a different graph. I mean, so we can't add edges, so in a subgraph. So what subgraph would you like to choose so that if we find a complete bipartite graph, so any complete bipartite graph we find has many edges coming out of it? What property of this subgraph would you like? Yeah, exactly, right? The same as we saw the other day. Right? We would like to start by taking a subgraph with large minimum degree, and then we know every vertex has lots of neighbors out, and there aren't many vertices up here, so each vertex must have lots of neighbors down. So what minimum degree can we guarantee? Average degree over 2. That's what we proved last week. So let's go back to the start. I shouldn't have called this G now, G prime. OK, I'm going to start out by, I can't use H either. OK, I'll start with a G star. Let's call it G star instead. Okay, so there exists a G star subset of G, so a subgraph of G, such that the min degree of G star is at least the average degree of G over 2. What's the average degree of G? Yeah, basically n over 4. Like a bit better than n over 4. Sorry, average degree of G is roughly n over 2. Right? Sum of the degrees is twice the number of edges. So this over 2 is roughly n over 4. Okay, so then every vertex here will have degree roughly n over 4 or higher. So we'll have n over 4 vertices going down here, more or less. So that tells the density across is at least a quarter. So is that going to be enough to prove this?
Like, isn't the minimum degree of the same order as the number of edges?
Yes, we lost a factor of 2, applying the lemma from last week.
But then, aren't you using that as a hypothesis? Isn't that n squared?
So yeah, the assumption is the number of edges is this guy, which means so the number of edges is about n squared over 4. So the average degree is about n over 2. Yeah, so we know as a subgraph of min degree at least n over 4. So is it enough? Is this going to be enough? Is this min degree of n over 4 enough to prove what we want? I mean, it's better than we had before. Before we had 0, but but is it enough? Can you make if the average degree is, if the density is a quarter, can you guarantee that left degree choose t times right degree choose t is bigger than 0? Yeah, you just go to 1, right? They could, every vertex at the bottom could choose one of the sides and send everything to that side, nothing to the other. Then you'd have density a half, and you still have 0, right? So it's not enough. And it sort of obviously had to be enough. We sort of threw away this factor of 2 when we really care about the constant here, right? Last time we didn't care so much about the constant, now we really do. Okay, so we need a stronger version of the lemma that we had before. So what's the lemma that we should choose? So the point about, so why was that lemma not strong enough? It gave us a very good lower bound on the min degree in terms of n, but that's not actually what we care about. What we care about is the density of our graph, right? It could be that the graph that we're going to work in is much smaller. What we want is the density of edges across is at least a half, or is strictly bigger than a half. Right? So starting with some graph with average with density at least a half plus a bit, we'd like to find a subgraph whose not its density is still at least a half, but every vertex has more than half the other vertices and neighbours. Right? It's not, we don't want an absolute bound on the min degree. We want a relative bound, a bound relative to the size of the graph left. Okay? And that we can do without losing the factor of 2. So let's state it. So if G is a graph with average degree D, there exists a subgraph of G with minimum degree at least what? So instead of average degree, I want to say it in terms of density. Sorry. So the density is just E of g divided by n choose 2. Let's call that, I called it alpha over there, didn't I? Okay, I'm not going to call this d, perhaps. What's a good letter? All right, beta. Yeah, sorry. So with m vertices and the minimum degree of G star should be at least the average degree minus epsilon times m. So let epsilon be any positive and is right? Okay, let's try and prove it and we'll see what we prove. I'm slightly confusing myself with the parameters. Maybe I want n large as a function of epsilon. Probably. Okay. So, what's the proof of this lemma? So you tell me, what's the proof of the lemma? Does the statement make sense first? Right, so given a graph with a certain density, which perhaps you can think of as being, so beta for us is a half plus alpha. Right? It's the density of the original graph. We're going to find a subgraph that still has density bigger than a half. So we want epsilon to be smaller than alpha. Right? And moreover, the min degree should be at least should be bigger than a half. Half of, so the min degree should be at least half the number of vertices. That's what we want. But m can be small. And so I should perhaps also say, so what you're now going to tell me is, pick m equal to 2. No, but it still be bigger than a half. Yeah, maybe I want m to be large as well. We'll see what happens. So what do you have to do? There's only one thing you can do. So just like in the proof of the other lemma, the similar lemma but the simpler one, there's only one thing you can do. Throw away vertices. Right? If there's a vertex whose degree is too small, m is only getting smaller as time goes on. Right? It starts out being n. If the degree is smaller than beta minus epsilon times n, or n is the current number of vertices, then you have to throw it away. You just keep throwing away. Okay? So what do we get? We get a sequence of vertices with the property that we threw them away one by one. So we knew that the vertex v1 had to be thrown away because his degree forward was at most beta minus epsilon times n. We know v2 had to be thrown away because his degree forward was smaller than beta minus epsilon times n minus 1, and so on. So how many edges does G have? Yeah, I can, rather than write density, I can just rewrite this as. Yeah, so perhaps I'm going to add in an extra. To make the statement more complicated, I'm going to fix an m0, and I also want m to be at least m0. So instead of going all the way to n, I'm going to stop when I get to m0. So how many edges does this graph have? Just count them. The number of edges of G is at most. Vertex 1 sends forward at most beta minus epsilon times n. Vertex 2 sends forward at most beta minus epsilon times n minus 1. So at most beta minus epsilon times the sum from L equals m0 to n of L plus whatever happened in here. We have no control over that. This could be a clique. So plus m0 choose 2. What's that? Well, how do you sum numbers from 1 up to n? You get n choose 2. Right, okay, minus whatever the ones in the bottom, but let's forget about them. This is at most beta minus epsilon times n choose 2 plus m0 choose 2, which is less than beta times n choose 2 if epsilon times n choose 2 is bigger than m choose 2, m0 choose 2. Okay. Epsilon n choose 2 should be bigger than m0 choose 2. Okay, and that was the condition. And this is a contradiction because that was our assumption, was that it was at least that. Okay, so there's nothing. The proof, once the lemma is stated, stating the lemma is the only hard part. Once it's stated, there's only one thing you can do, and then you just count. Right? Is it okay? Questions? Does everyone understand the statement? If not, please ask. And does everyone understand the proof? If not, please ask. And thirdly, does everyone understand why this was the only thing we could possibly do? Right? There was no choice in the proof. There was no cleverness. You just do what you have to do and go, that's the answer. Right? Yeah?
Can you remember what was different from this one and the last lemma we proved?
Last time, so the lemma we proved last time said that if the average degree of G is D, implies there exists a G prime with min degree at least D over 2. So we lost a factor of 2, but we got a bound that was in terms of D. Right? Here we don't have that. We don't have a bound of min degree that has anything to do with beta times n. N has vanished. M could be much, much smaller. Right? I mean, all we know about M is it satisfies this.
Why is the minimum degree of G star going to be bigger than E minus epsilon? I didn't see G star exactly.
Oh, sorry. Why is it contradiction? So.
I get it why it's a contradiction
Okay.
of values of G.
Yeah.
Why are you going to have the minimum degree of G star bigger than?
So right. So the contradiction said. So suppose this process continued until we had only m0 vertices left, then we get the contradiction.
Okay.
So the process must have stopped earlier. So the point at which it stopped, we could not choose a vertex with this property. So therefore, every vertex had at least beta minus epsilon times.
And it will have more than m0.
Yeah, because you stop before this point. Exactly. Exactly. More questions? It's okay? Okay. So why are we now done? What's the proof? So I've told you all of the pieces. Now we just have to do them in the right order.
This time the graph that was missing does exist.
Right, so what do? So maybe I'll get rid of this as well. Is this okay? Can you erase? Okay. Right. So first step. So we've got this graph G. Edge is least a half plus alpha times n choose 2. We apply the lemma. Implies there exists a G star in G. So it's got m, which is bigger than m0 vertices. Right, so what are we going to pick? M to be m can be much smaller than n. All we really want is epsilon is we could put epsilon to be alpha over 2. Let's put epsilon to be alpha over 2, let's say. And then m0 should be, I don't know what, alpha times n or something. Right. Whatever. So m0 is some small constant times n. So it's got lots of vertices. I mean, we could take m0 to be square root of n if we want to. Maybe I'll do that just to make it really obvious that nothing is happening. Right? And the min degree of G star is at least, what's beta? Beta is a half plus alpha. So it's at least a half plus alpha over 2 times n. Right? Okay. Now, the induction hypothesis implies there exists a copy of KQQ in G star. Right? Because G star has density a half, at least, and it has lots of vertices. Right? Where Q is chosen to be some function of t, large.
Sorry.
Yep.
It's because we had that alpha is the king, right? It's,
Alpha is the, so what's that?
it's middle of 1, right?
Yeah, some arbitrarily small constant.
somewhere.
Yeah.
But the problem is if it decays with n,
Uh-huh.
maybe epsilon times n choose 2 is not bigger than
Than n?
choose 2.
So it would have to go to 0 very fast, right? Yeah, but I'm not letting it decay fast. I'm choosing it to be fixed. So alpha and t are fixed. Alpha and t are fixed. And n tends to infinity. And if I can do it, if I can prove for every alpha and every t, I claim that I've proved the theorem. There's enough to prove little o1. Because you just need some to go to 0 at some rate. It doesn't have to be fast. Okay. Is it okay? Okay. Okay, so alpha is arbitrarily small constant, t is an arbitrarily large constant, but constants, and n depends on both of them. So in particular, q will depend on both of them. Okay, so q is another large constant. This is the kqqq that we're finding in G star. Yeah, so I know that at this point, when you're not used to thinking about these things, this point in this proof, it gets very confusing. So please don't worry if it's very confusing. It's totally normal. So I did warn you at the start that I didn't really expect you to necessarily follow all the details. So if you are following, that's great. If you're not, please don't worry. This is more complicated than the other proofs in the course. And this one is not examinable. Right? I'm not going to expect you to reproduce this proof. Okay? Just kind of let it wash over you, and right, you could be like what are the people in the rivers getting gold, right? Just like wash over you and like try and pick out some nuggets, whatever. Right, so we found this QQQ, and now we're back in this picture. Right, now we're back here. Except this universe now is this G prime is G star minus this KQQ. Right, this whole world is G star. And the KQQ is also in G star. And so what do we know? We know every vertex here, how many edges does it send down? Well, at least this many minus 2q. Good. Minus 2q. But q is a constant, and m is bigger than root n. So this is at least a half plus alpha over 3 times m. Okay.
Sorry, are you counting for both potatoes or only one?
I'm saying any vertex. So just a single vertex sends at least this many edges down here. And how many vertices are there here? M minus 2q. Yep.
Sorry,
Yep.
where did that 3 came from?
This 3, it's bigger than 2. It's just saying that m is much bigger than q.
Oh, okay.
Right? Or alpha times m is much bigger than q. Why? Q is a constant, and m is bigger than root n. Yeah, so m is much bigger than q. Yeah. More questions?
Why is not Q? Why is 2Q?
Oh, because it can have edges inside as well,
Ah,
which we're just ignoring. Right? We're not using them, but they can exist. Okay? Okay. So, now we're almost done. We just need to bound this thing. So we choose a place to do it. Maybe here. Sum over v in v of g prime, degree left of v, choose t, times degree right of v, choose t. We just want it to go to infinity. So we don't really care what these numbers are. We just care that they're both at least t. Right? So it's at least the number of vertices of G prime such that degree left of v is at least t and the degree right of v is at least t. Right? Take a silly bound. So I'm just bounding these by, replace these by 1 or 0, just 1 if they're at least t. And even sillier, this is at least the number of vertices in Vg prime such that the degree of v is at least what? What degree do you need to guarantee that left degree and right degree are both at least t? Yeah, q plus t, exactly. So all I want I want there to be a large number of vertices whose degree is at least q plus t. So let's let x be the set of vertices such that the degree of v, degree of v left plus right. I mean the degree up. And let's suppose that this thing is bounded by a constant, so it's small. So I claim there's a contradiction. So what should I count to prove that this is a contradiction?
The number of edges?
Yeah, exactly. The number of edges between top and bottom. Because what do we have? We have a lower bound from this, and we have an upper bound from this, and they're going to contradict each other. So let's just do it somewhere, somehow, maybe here. Right. So the number of edges, let's call all this A and all this B, just so I can say edges from A to B. So what's this at most? So counting from the bottom, we have a bounded number of vertices with arbitrary degree. Maybe I'll call this C as well. So it's at most 2q times x plus q plus t times m minus 2q minus x. Right? So the vertices of x can send as many as they like. The rest of the vertices can only send at most q plus t. And I don't care about equals or, we're going to win by miles. Okay? What is at least? It's at least, each vertex here says at least this many down. So it's at least a half plus alpha over 3 times m times 2q. Right. So let's just cancel things. So we have a q times m. Let's bound this first. Let's be silly. So 2 times c times q plus q plus t. I think I just do times m. Right. Let's just ignore the fact that we gained a bit here. Also don't care. Okay. So there's a q times m and a half times m times 2q. So they cancel each other. What I'm left with is 2 alpha over 3 m times q is at most t times m plus 2cq. So why is that contradiction? Yeah, I feel like I'm... right. Q is much bigger than T, exactly. M is much, much bigger than these guys. So this thing doesn't matter at all. It's just these two fighting it out. And we just want to choose Q to be bigger than 3T over 2 alpha. Okay, so not even that big. Just somewhat big. Right. Maybe I'll even make it 2t over alpha. So we have a bit of space. Okay? So it's a contradiction. So then x isn't bounded. So then this thing does go to infinity. And so we get a contradiction. So we're done, right? This thing goes to infinity means, so by calculation that I guess I erased at some point, perhaps I'll do it again. Okay, so this was to show, this calculation shows that this really does go to infinity. Right? And then what was the other part of the argument? Was I counting? We were counting cherries, right? So the number of these things, t, equal to the sum over v in g prime, degree left of v choose t, times degree right of v choose t. We just showed that this goes to infinity, as n goes to infinity. And if there's no copy of k, t, 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 that implies the number of these things is at most what?
T minus 1,
Exactly. Right? Which is a constant. So this thing is a constant, and it's bigger than something that goes to infinity, and that's a contradiction. Okay? So the proof is really just a more complicated version of the Kövári-Sós-Turán theorem, plus this simple to prove, but maybe slightly tricky to state lemma. Yeah? Uh-huh.
So we get a contradiction, but how do you get to the original statement of the theorem?
What do you mean?
I mean, we have that the Erdös-Stone theorem.
Yeah.
That statement.
Yeah.
So we have that there is a
Yeah, so we found a KTTT
yeah, okay.
in this graph.
Yeah.
So for any alpha and any t, we've shown if n is sufficiently large, a graph with this many edges contains KTTT. So for any h, so the first observation was any h with chromatic number 3 is contained in KTTT. So if for any alpha, so whatever tiny constant you put here, and any h, if n is sufficiently large, then you're at most this thing plus alpha. It's true for any alpha, and therefore it's true for little o1. As n tends to infinity, this alpha tends to 0.
Yeah, that's still for me, the little thing, because...
Okay. Yeah, so maybe let me say a bit more about it. Yeah, so this really means when n tends to infinity, right? The same thing as so for all epsilon, this holds for all n sufficiently large as a function of epsilon. Right? So this is just shorthand for this statement. I mean, you can also restate it as, right, if you do extremal number minus c times n choose 2 divided by n squared, it tends to 0. It's also the same thing. Right? It's just whatever rewriting limits with epsilons and deltas. Right?
How was our upper bound again?
So this was the upper bound.
No, sorry.
The lower bound was just take the Turan graph.
Yeah.
So with the lower bound, you could take epsilon basically actually equals 0, right? So in this case, in correct number 3, it was just this. Sorry, what we're talking about. It's just a complete bipartite. So it literally n squared over 4. So the lower bound is n squared over 4. The upper bound is n squared over 4 plus little o n squared. And if you try harder, then you can even prove that it's n squared over 4 plus n to the 2 minus epsilon for some positive epsilon. So it's really little o goes to 0 reasonably fast. Mm-hmm.
Our proof was by induction, right?
Yeah.
On R.
Yeah.
Can you remember when we used the induction?
At the so at the point where we found KQQ. Yeah, so what's the proof for general R? For general R, you do exactly the same thing, except instead of finding a KQQ, you find a KQQQQQQ, right? An R minus 1 uniform Turan with each of size Q, and instead of counting pairs like this, you count things like that. Right? You just count things going to 1. And instead of having the bound being Q plus T, you want it to be sort of Q times R minus 2 plus T. Right? You might be going full to everybody, and you want the last one to still have enough. And this bound is exactly enough to give you that. Right? This is exactly just enough to guarantee that you can't fit all of your neighbors inside all but one of the blobs. You have to send some to the other one.
We would also need Turan's version for KQQQQ n time, right? We wouldn't need it? Because we needed that bound for KSD.
No, sorry, that was an induction hypothesis. So this is what we're proving.
Yeah.
So we're proving that the induction hypothesis says that we can find this KQQQQQ, this R-partite, complete R-partite graph. Yeah. So it's not Turan's theorem, it generalizes Turan. Okay,
Yeah.
not exactly because there's an error term, but right. But that's what we're finding. We're finding inside this G star, we're finding this thing that's 1 smaller. So the proof even looks a bit like the proof of Turan that we had, right? But there we picked out, when we were proving Mantel's theorem, we picked out an edge and we counted edges across. Right? It sort of looks similar. Right, so next time, yeah, so don't worry if this was a bit confusing. I wanted to give you an idea of how this was proved. I want to talk a little bit in the last few minutes about bipartite graphs, because I forgot to the other day, and because right, for bipartite graphs it doesn't really prove very much. This. So what's the situation for bipartite graphs? So I'll put back this theorem. So I mentioned that this was sharp for S equals T equals 2. Right? For C4, this was sharp. We don't know if it's sharp in general.
How sharp?
Sorry?
How sharp is
So for C4, the number is actually known exactly. So not only the constant is known, but really the exact value is known. So C4 is a very special case where really people know everything. This is due to work of Szemeredi about 20 years ago, maybe even 30 years ago now. But for other bipartite graphs, then things are wide open. So what's known? So it's known that if t is bigger than s minus 1 factorial, then the extremal number of kst really is order n to the 2 minus 1 over s. So in particular, it's true for k2t, for any t, and right, so and if s is large, for k, so it's not known, so open problem, prove that the extremal number of k44 over the extremal number of k33 goes to infinity. Right, the best construction we have for k44 is take the construction of k33 and add a bit, which is very strange. So I think most people believe that this really is true for all S and T. We don't know how to come up with constructions. And the constructions that are known are algebraic. So our knowledge is limited by the fact that we lack these algebraic constructions. We don't have any systematic way of producing them. Just recently, a more systematic way was introduced by a guy called Boris Book. And this was used by him and some other people to reprove this with a worse constant here. So he did it in a less, so he's still using algebra, but in perhaps a more flexible way, but unfortunately it gives a worse bound. Here's another simple example, perhaps to show really what the limits of the knowledge are. So the extremal number of the even cycle is at most some constant depending on k times n to the 1 plus 1 over k. And this is known to be equal to this guy up to a constant factor if k is 2, 3, or 5. And that's it. Right, so these algebraic constructions exist for C4, C6, and C10, but we don't know how to produce them otherwise.
Why C8 is an exception?
So that's a question to ask someone who understands algebra, which is not me. Yeah, so they're just sporadic constructions people have found using known constructions from algebra. So whether or not something exists for C8, I mean, it might be that it doesn't exist for some weird algebraic reason, and actually this is not the right answer. I mean, who knows? Huh?
So for example, suppose like someone were able to improve that and prove it for t smaller than factorial.
Yeah.
Like, do you have any idea how far you'd be able to go? Like,
I mean, it could be always true. I mean, if you asked me to guess, I would guess that it's always true. But it's not a very educated guess. It's just, I mean, what the hell else are you going to guess?
I found it strange that it doesn't depend on t then.
So the question is just, do such algebraic constructions, the algebraic constructions, they're very regular. So you need to find a graph that comes from some algebraic object that has this kind of extreme regularity properties that it's difficult to construct such things. You might try and construct them randomly, but random things vary too much. These things are really extremely rigid. So, do they exist? If they exist sometimes, why shouldn't they exist always? Well, perhaps there's some reason. Perhaps there's some sort of deep algebraic reason that I am very far from understanding. But I've just I have no idea. I mean,
But I think what I was asking is,
yeah.
if that were true for all S and t,
Yeah.
it had to be symmetric, right?
Oh, right. Oh, sorry. So, I mean, yeah, sorry. With the theta, it's S is at most t. Yeah, sorry. Yeah. Otherwise, 2 minus 1 over t. Yeah, sorry. Yes, there's a few other things. So there have recently been some interesting developments with this method of Boris Book and with David Conlon. They proved that they proved null conjecture, which said that for every rational number, there exists a family of graphs whose extremal number is order n to the a. So for every rational number, there exists something with this property. But these families are sort of weird. You take some tree and you take lots and lots of copies of it, and they can intersect in crazy ways. Yeah, so there's lots of really nice open problems related to in extremal numbers of bipartite graphs. Mostly this subject has been stuck for the last few decades. Like really, not so much progress has been made on these particular numbers, but some interesting progress has been made recently in sort of pushing in slightly different directions. So next time I'll tell you. Maybe next time? I don't know. At some point we'll talk about some different directions, some different kind of questions you can ask about the extremal properties of graphs. Maybe, yeah, I'm not quite sure what I'm going to do next time. Maybe I should tell you some more Ramsey theory first. Let me tell you a little bit. Yeah, and then we'll come back to this a bit later. Right, anyone who didn't